Good afternoon, everyone, or good morning, good evening, wherever you are in the world. It's Brendan Chaplin here from Strength and Conditioning Education. And welcome back to the International Meeting of the Minds Conference. We've had some wonderful talks so far this week, and we've got some superb talks to come as well. And really excited to introduce Mladen Jovanovic to the conference lineup today. It's a pleasure to be able to connect with Mladen, having followed his work, and you can't miss him because he puts out such good quality content all of the time. It's great. So welcome, Mladen. How are you today?
Hi, Brendan. Thanks for having me over.
It's a pleasure.
Really good. Thanks for having me.
Good. Well, let's crack on. I'll hand it over to you. Really looking forward to your presentation, GPS applications in team sports.
Okay, thanks a lot. Anyway, let's start. I'm going to give you a quick presentation about the GPS application in team sports. I kind of organized it in a tree manner. So these are the topics we're going to cover for today. We're going to start with the left tree and proceed to the uses part of the tree. But before we go, I want to give you a couple of introduction and assumptions we're going to have with the GPS analysis anyway. So introduction and assumptions. First one is I like to mention the core message as a performance analyst or GPS analyst. These are a couple of things we need to keep in mind because GPS also corresponds with the overall data collect. Everything we collect needs to be kind of integrated, and GPS is nothing special. So we need to keep a couple of core principles in mind when we deal with GPS as well as with any other data collection. So first one, I really like this quote from one of the books from Vital Smarts. Is the only reason why we gather and publish any data is to reinforce vital behaviors. And sometimes we usually forget this message. Sometimes we just end up collecting data because of just collecting the data. So we need to kind of remind what's the point of actually collecting, what we are trying to modify or reinforce in our squad. Next one, this is a picture from a Fuzzy Toolbox from MATLAB, pretty much explaining the, as I like to say, a difference between a scientist and difference between a coach, or basically what does scientist provide on the left side and what does coach want. So we want to simplify things and make things easier to kind of make decisions in a real life. And as I said, GPS is as well one of the parts of all the numerous data we collect. And I highly suggest checking this book by Ben Alamar regarding all the data analytics. And as I said, we need to integrate the data, GPS as well. And this is one very interesting graph. So all our data, including GPS, needs to be standardized, needs to be stored in a centralized location, and need to be integrated. Now it doesn't seem so important, these three circles, but as I go, I'm probably going to return back to some of these concepts, especially standardization and integration. A couple of things we want to avoid is the elephant in the room. Sometimes usually use charts and graphs to back up our coaching or anything, and we sometimes just miss the big elephant in the room, and that might be athletes as persons, might be a team culture, might be potential of our players. So let's have a big picture. Don't really focus on only GPS metrics and only nice parts and charts. Try to see this guy also in the room as well. Pretty similar. I call this is a picture from Allegory of a Cave from Plato. Pretty much saying same thing. we are not seeing the real world, we are seeing the shadows of the real world, and sometimes we get too much focused on shadows of the world, just forgetting that the training and coaching is not bars and charts, you know. Just keep those two in mind. I'm going to quickly just go over my expertise in quotation marks. First of all, I think I see myself as a jack of all trades, master of none. I've been coaching for some time, and last couple of years I've been doing data analytics. So I've been learning programming in R, machine learning, and statistics in general. But I'm not expert in any of those areas. So one thing I see myself is basically as a bridge. So I can kind of talk two languages, and that's from two domain expert sides. One is coaches and athletes, because I understand some of the things these guys want and how do they interact and communicate. And I also understand how the programmers, researchers, and data scientists think, because I know a little bit of both sides. When we talk about GPS, we usually talk only about physical aspect. And I see all team sports as a continuum between track and field, which is mostly physical. There's no decision making, and chess, playing chess. So most of the team sports fall on this continuum. So we need to keep this in perspective, and not everything in team sports is physical dominated. Some of the sports are quite mental, quite cognitive, and this good performance in team sports most likely is determined by a good decision making and being game smart. Another thing we need to consider quickly is the validity and reliability of the GPS. So for this presentation and for everything that follows, I'm going to assume that all the GPS metrics are valid and reliable and sensitive, but as we know, and as the research shows now, there's a lot of typical errors. There's the differences between manufacturers of GPS. Even if you update your software in a GPS, you might get different metrics. So as with everything we do in training and modeling, we always have some assumptions. The assumptions are very important, but in this case, in this GPS talk, we're going to assume that all the GPS metrics are valid and reliable. Let's talk a little bit about planning to use the GPS. As I said, as with any data, we need to have good planning, and GPS is only one part of all the data we collect. When it comes to plans, I usually split the planning into top-down and bottom-up approach, and I believe that the best solution and optimal solution is just reconciling both top-down and bottom-up approach. In this case, as you can see on the left picture, global plans or top-down correspond with like a big scheme, big vision, and bottom-up is basically building from small blocks and just going up. But let's go a little bit deeper in a bottom-up approach. So if we start building a bottom-up and just increasing complexity without a big plan, we might end up doing this. So we start at the bottom. We have the tools at the given level, and we try to do best what we can with those tools and in a certain context and the elements on hand, and we slowly build up over time, but without a big picture, without a plan, systematic plan, we might end up building on a very, very poor structure. I saw this a couple of times, especially with the data as well. We start collecting data in Excel, and team spreads out, people continue collecting in Excel, and basically things start showing his ugly head because Excel was never meant to be a database solution, and down the road things get very, very slow. Collaboration between team gets very weird. So it comes back to this to the picture I showed by Ben Alamar about centralizing and integrating the data. So bottom-up approach basically try to answer some of these questions. How do we collect? What do we collect? How do we process the data? How do we integrate it? How do we visualize and how do we communicate? One important thing to consider is something that's called metric engineering. Basically, we also need to think what metrics are important. If we don't have those metrics, how we can engineer them. I'll go back to this concept during the uses presentation, especially covering stuff regarding the metabolic power and something I like to call worst case scenarios. And again, there's no free lunch, as data scientists like to call in machine learning. So even if you have the best algorithms in the world, if you have bad data, you're going to get bad results. So garbage in, garbage out. Top-down approach is basically starting with a vision, starting with a plan. Why are we collecting the data in the first place? Let's remember the first slide saying that the role of all data collection is to reinforce crucial or vital behaviors. So we need to know what we are trying to influence and how is that going to affect the vital behavior and decision making, how are you actually going to use the data. Sometimes when I speak to people who are actually collecting a lot of data and GPS and everything, you give them a simple question. It's like, what did you modify? What training decision did you make based on your data? And usually it's a mute. There's no response. So we end up really focusing on a bottom-up approach, like hamsters collecting a lot of data, digging a deeper hole. But we don't see a big picture. Exactly why are we collecting and how is that going to influence our training? It's also very important to avoid paralysis by analysis. And one main, I think, crucial aspect of data collection is to bring new food on the table. So most of the data we collect is basically historical data. It just confirms what we already know. So the goal of the data is also not to be only descriptive, but also prescriptive. So it gives you something new, something that you didn't know already. So that basically covers some of the warnings I want to say before actually going to uses. So when it comes to GPS uses, I'm going to start with the drill classification and go down to real-time fatigue assessment, and these are most likely sorted from the most easiest to the most hardest, and from the least time consuming to the most time consuming, and basically from less expensive to more expensive. The first one is drill classification. So basically the goal of drill classification is to create a database of the drills. What drills are similar, and basically what's the optimal number of groups of drills. And once we do that, for example, we might have each coach might have maybe around 20 training drills that they like to use, and we are interested in, do these drills differ, and in what metrics do they differ, how are these drills similar, and what metrics do these drill kind of overload. So some of the drills might overload speed or high intensity bands, and some drills might overload high acceleration, high deceleration. And again, this is the lowest level of the use of GPS. I think most of the time also not done properly or not done at all. And I think it's also very useful when prescribing training. the funny thing is that for this task, you don't need to buy GPS units. You can, because you're not going to use them for a year. You're probably going to use it for a couple of months. So you can probably borrow some of the units, and after you collect the data, you can return the GPS unit, right? Again, when it comes to drill classification, it's more art than a science, because for example, most of the GPS vendors give you around 200 metrics. So for every individual, every training period, you get around 200 metrics, and that might include distances, time spent at certain zones, number of acceleration, number of decelerations, and all the different metrics. So the problem is what metrics to choose, which metrics are important, what metrics, I'm gonna go later on about it, is what metrics are similar, what metrics are telling you the same story, and basically how you're gonna aggregate the individual performance into drill performance. This comes back to statistics, because for every drill, we might have 10 athletes doing one drill, and then we have 10 athletes doing another drill, but to create a drill classification, we kind of need to aggregate individual performances into a drill. So, and also once we do that, it completely different. Actually, we might get completely different results depending on the method of clustering we use. So there's a great paper by, I got this paper from Morgan Williams, and it's actually, they did drill classification in Australian football rules, and this is quite useful to read. It gives you one perspective of how these guys are done it. Usually the researchers, the traditional statistics guy usually use ANOVA's analysis of variance to kind of classify the drills, but that's only taking one GPS variable. And as I said, most of the GPS vendors give you around 200 metrics. So we need to use methods such as K-means clustering or hierarchical clustering to try to find the similarities between the drills. This is a heat map from actual GPS data. On the right, that's blurred. Those are training drills, and at the bottom we have GPS metrics. And heat maps kind of give you a visual story of what drills are similar, and what actually, in this case, also what metrics are similar. In my case, this is not the best way to visualize, and it just makes you confused. It looks nice. People think, oh wow, colors and a plasma, but it's not very useful. This is a sample of for six GPS metrics. In this case, this is a total distance, the distance doing jogging, low intensity, medium, high, and distance accelerating. Again, these are 6 GPS metrics out of 200. And on the left, we have GPS drill. On the left, the blurred, those are our training drills. And what we can see is each dot represent performance of a given individual, of a given athlete. And as can be seen, they spread. They are not, focused on one spot. And as I said in the beginning of a clustering problem, we need to figure out a way to kind of aggregate the individual performances for a given drill. In this case, I use median. So the vertical lines represent the median, in this case, distance, total distance covered per every drill. And as you can see, there's a lot of overlap between the drills. It's not that black and white. Some players might perform similar in all drills. Different players might differ across the drills. So again, it's not that black and white. So even if you use averages or mean, you also need to take individual variation into account. And this again might be a problem for mixed modeling, which is something I'm trying to read more about. As you can see, these the colors are actually a result of the clustering. So in this case, we have let me count five clusters of drills, and each different type of drill is colored differently. And this also gives you a quick visual to see how these types of drills differ in terms of different metrics. This is just one of the visualization, and in this case it's also good to see how much things overlap. Again, this is hierarchical clustering. Same thing, based on something that's called distance between drills. We try to find the clusters that are similar, that are close by, and we group them together. And again, the results for our hierarchical clustering depend on the method used. So it can differ. We can try multiple methods and see which one is most logical. And in this case, you can see there's 5 clusters. Again, you can cut the drills and split them on more or less. And again, we can probably see here that there's one cluster or 2 clusters. This is the one, and this big one is number 2 cluster. And depends how many clusters we want to extract. We can do it, and depends on what's useful for us as a coaches. So again, back to a second slide where I show the difference between someone who's doing statistics or research and someone that wants concise information, very strict, very simple. So second thing that we can consider when we use GPS is metric classification. So metrics classification is similar to drills classification, but in this case we are trying to minimize the number of GPS metrics. So as I said, we have around 200 metrics, and we are interested if those metrics are measuring something that's similar, or in this case we call it latent variable or hidden variable. One of the ways to try to extract those different variables is to use factor analysis. We can also use latent variable modeling and also a cluster analysis. So we want to see, do these metrics also cluster? Are they correlating between or and not correlating with other? So, for example, all of our GPS metrics might measure 2 latent variables. Might be as I think Dave Tenney uses velocity load. So those are metrics that correspond with the velocity load, and we might have GPS variables that correspond with the body load or something that's related to change of direction. One goal of this metrics classification is to reduce the number of variables we need, and we need to communicate and we need to visualize. We also want to combine the drills classification with metrics classification to see do the drills or drills types overload different latent variables. So, for example, we might have the drills that overload time spent in a high velocity zone. We might have drills that overload change of direction, or we might have drills that are very much overloading the deceleration. So again, the goal is to give us something that we can use, something that we don't already know, and so we can actually use this to prescribe the training, not only describe, but once we have this drill classification, we can basically return our GPS units and get more insight into the drills we are using, and just use those as building blocks depending on what training effect or what GPS variable or physical variable we want to overload. Again, this is also heat map, but in this case, both vertical and horizontal are the GPS variables, and the heat map shows the correlation matrix. So correlation is just showing you, and as you can see, the diagonal is ones, so the same variable correlates perfectly with itself. So what you're looking for here is to see kind of groups of variables. It's pretty hard to do it for 200 metrics, so that's why we use hierarchical clustering to help us to find the groups instead of trying to do by ourselves, visually. So again, we want to find something new, something we don't already know. One of the problems, and again going back to the assumptions that I mentioned in the beginning, is that we are too much biased to a physical aspect of things or aspect of drills, and not everything in team sports is physical. If we can also plug in technical aspects, or maybe in the near future also the decision making that's happening inside the drill, we can also maybe cluster the drills based on a cognitive aspects, which one maybe overloads more cognitive, what drill maybe overload more physical. In this case, just to help the coach to be able to prescribe training drills with some data backup. Basically, we know this is happening, and that's why we are prescribing this drill. So basically, just to say, is this drill doing what we thought it's doing? And as I showed on the graphs, things are not really separable. So there's a lot of overlap between the drills, and most coaches know that, and that's why we need to have multiple. We need to have a database of the drills, and depending on our tactical goals, we might select different drills that might more overload certain physical quality. So just a thing to basically to remember. And as a natural way to continue this talk about the drills and metric classification is this basically classifying things based on a position and trying to provide a position-specific work. So in my opinion, as additional factor in drills classification is a position play. So what we are trying to answer in this case is there a difference, at least in this case in physical term, is there a difference in physical performance between positions in a game? Are the positions demanding different, do they have different needs in terms of physical aspect? And is there a difference basically between physical qualities between positions? By physical qualities I mean more something that's measurable, maybe a maximal speed, maximum aerobic speed, height, body weight, and all that stuff. So we basically have game demands, and we have in qualities. So we try to reconcile those two to see if there's a real difference between game demand in terms of GPS data, and if there's a difference in the terms of what qualities the positions possess. And I said, as I said in the beginning, garbage in, garbage out. It depends what we measure, how we measure it, how it, how is it reliable, and is it sensitive, and so forth. So we need to keep that on mind as well. We going back to metrics classification. We are interested in do positions played differ in different latent variables as we extract them from multiple GPS variables. So let's say do central back demands more high velocity, or the fullback or central defender, they see performing less when it comes to velocity, but performing more short sprints, a lot of more accelerations or decelerations. So yeah, exactly. We are trying to find what's the physical quality they differ in terms of the need or expressed physical quality. And combining this game data, we are trying to combining this game data with the drills database. We want to see if our drills are actually overloading these latent variables per positions. So again, do drills performance differ based on position played, and do drills performance differ based on individual qualities? So again, this is just with all our modeling. This might be an extra factor that we need to put into a model, and we need to see do the drills. So when we do a drills classification, we basically classify drills regardless of the position played. So we put all our players in a bin. Everybody's inside. What we can also do is to classify the drills based on a position. So basically, then we have 5 or 6 models, and then we want to see are the drills different based on a position played, and that helps us basically preparing our players more specifically for a game, assuming that there's a difference in terms of physical performance inside the game. So yeah, same thing as I said before. We want to answer, do our drills provide enough of overload based on positions played and physical qualities? And where do they provide overload, in what metric? And how do we need to complement the training? So basically we want to see what physical qualities or latent variables we are overloading with our drill, and what we need to complement with maybe more generalized training, maybe doing extra sprints, maybe doing extra conditioning. And again, we are still focusing only on physical side of things. One thing also to consider is the also worst case scenarios. Sometimes we are too much focused on the average, and what we need to take into consideration is to prepare for our worst case scenarios. So there's also need to be a way to extract the most difficult part of the game or most difficult part of the drill, depending on a position. So we prepare our players for something that's the most difficult. And I really like this saying from Anti-Fragile book by Nassim Taleb: provide for the worst, the best can take care of itself. Something to ponder about. Training load. Training load involves. I'm gonna talk about training load, and I'm gonna cover a couple of components. This is just an overview. Training load is something that a lot of people are interested in, and I'm just gonna give you some of my ideas about what it is and how we can. What's the different ways to use and calculate the training load. The most easiest thing we do at the moment is to use absolute zones. So absolute zones refer to any type of GPS metric, so velocity, acceleration, or metabolic power. So we kind of a bin velocity from, for example, low speed, medium speed, high speed sprinting, and we say how much time did you spend in a certain bin, how much time did you spend in sprinting, how many reps did you do in a sprinting velocities, and so forth. So one thing to ask is how do we decide on the cutoffs? Like, why is that velocity as it is? So why 19 kilometers an hour? Why not 20? And so forth. And one thing to consider is should we completely avoid the bins? I'm not so sure. We can still use the bins, but we can also provide something that's similar to Bike Score. And Bike Score is a brainchild of Philip Skiba, applied on a cycling. So basically, they try to summarize the whole performance of the session and give it a kind of like a training load score. And it's not just the average. They applied certain filters and rolling averages, so they kind of put more weight to more intermittent stuff and take more into account the high intensity training. I can easily provide you with the link, but you can also Google it, and you can find some applied papers on how to do it with the Bike Score. And again, what do we consider as a training load? What's the gold standard to training load? Is it distance covered? Is it high speed running? Is it number of accelerations, number of decelerations? The question is like, how do we know that's the best variable to describe load? And one more practical thing we can try to do is to maybe do a data mining and modeling to find the best variable. And again, this might be different between sports, might be actually different between the athletes. So as they say in the machine learning, there's no free lunch. One a little bit more complicated level might be a use of relative zones. So by relative zone, I refer to using some zone that's related to individual physical quality. It might be maximal sprinting speed, might be maximal aerobic speed, critical velocity, or velocity at the threshold, whatever. So we use those drills thresholds to set up the zones. So instead of setting up the absolute zones like 19 kilometers an hour, 14 kilometers an hour, we set up the zones, the thresholds based on individual qualities. And I think there are a couple of papers showing that this is a little bit better than absolute zones. But absolute zones are better when you compare individuals. So when you compare individual performance, so you want to compare player A to player B, or squad A to squad B, squad A to squad B. But the relative zones are more important when we want to quantify the individual training load. For example, if my maximum aerobic speed is 14 and someone has the maximum aerobic speed at 16, and we both run maybe 2 kilometers in a high velocity zone, is that the same? I mean, is that a same stimuli for both of us? Is that the same load for both of us? I would say no. So I think using relative zones is a little bit is a step forward compared to the absolute zones. Again, it comes back to top-down approach. First we need to know what are we measuring and why are we measuring, how are we going to use it. So in this case, relative zones might be better when we want to see the individual load, basically how much stress does a given training produce for a single individual. And again, how do we know what threshold is important? Sometimes we say we just pick some random threshold, might be velocity at VO2 max velocity, might be lactate threshold velocity, but how do we know that zone is actually important or that threshold is important? Because just because there's a threshold, I'm not so sure it is basically important. And we might say that, yeah, time spent in high intensity zone is the one that's actually producing results or maybe improving aerobic endurance, but we need to validate it. So we need to kind of model it, and I'll go back to this topic when we speak about Bannister impulse response model. So what we are trying to do is to see if our metrics of load are actually corresponding to any real phenomena. So that might be related to improvement in maximum aerobic speed, might be improvement in actual game performance. So again, as with absolute zone, relative zones are a step forward, but we still need to validate what's the best threshold, physiological threshold to use. And there's another problem. This is a step function, just a random picture, but step function means that, for example, we keep track of a training load that are relative, and our player for first 3 months have maximum aerobic speed at 16. So we set up the threshold at 16, and from, let's say, 3rd of March, we retested his maximum aerobic speed, and his maximum aerobic speed now is 17. And then we basically have a step in our function, so from 16 to 17. So we're going to use 17 as a threshold. So if we kind of visualize all the training loads over time, the moment when we start using the new level, going to affect all the metrics down the road, and basically it gives us like a glitch or like a cut in a training load graph or chart, and that's related to us just switching to actual a new level instead of changing training. So that's one of the problems with relative zones, because they change, and that the quantification of training load might change abruptly, which is not the case with absolute training zones. So again, the potential solution might be to track both, and just being smart which one you use, and use your testing as a context, so you switched from last test to a new test. Game as a context. With any metrics, it's important to have a context. For example, this is one random metric from one of the GPS analysis we use. I have no clue what it means, to be honest, because it's one of the 200. And this is just a random picture, but the name of the variable is real. So what does it mean? Is this good or bad? Is this improving or is not improving? Is it meaningful change or not? So you cannot basically tell that from this graph, because you don't have any context. You cannot compare it to anything. One simple solution is to basically provide the average of that metric, especially if you're dealing with some new metric you're not familiar. You don't have a kind of a sense of it, or like a feel for that metric, so you don't know what's good or bad. So just providing a simple average or a baseline for that metric, it might be better for someone who's not used to this metric to kind of get an idea what's happening. Again, this is useful, but it's still not enough. What we can do is to provide also the average or some baseline for the metric, and also provide some form of a zone, and in this case that zone might be standard deviation, or might be 25th or 75th percentile. So in this case we also get a feeling for a baseline, but we also get a feeling for a variability of the metric, so we know how this metric is variable, because we might have the same average, in this case 15, but the variability of the metric might be huge. So we are within within basically normal variability of a metric. What we can use to, especially if you're not familiar with a metric, is to use a game as a context. So we probably can agree that the game is the toughest load in a week. So we can use that to give some idea about the training load. So we can use a game performance to tell if a certain training session was hard or easy, just because we can compare it to a game. Since a lot of metrics in GPS metrics or physical performance metrics in a game have a high variability, I think up to 15 or 30% for some metrics. So from game to game, we might get huge variability, and on a certain game, you might do 1,000 kilometers or 300 meters sprinting. On some game, you might do 400. On some games, 200, and that's just a normal variability inside the game. So we can use that as well to give some idea how training is hard. So yeah, one thing to do is we normalize the training load based on a game load, and that gives us some idea of how hard was the session. As you can see on this table, this is from one of the reports I used. You can quickly see the columns. Sorry, the columns are different GPS metrics, and in a normal color is the actual value of that metric for each individual. Each row is a different individual, but it also gives you a kind of percentage of his usual game performance, and then you can see who performed. You can see if overall, you can see if the session was very hard compared to a game, and then you can see if the session was hard per individual. So you can quickly pinpoint to a guy who didn't perform well, or it might not be the case, but for example, for the guy who the drill wasn't enough or wasn't providing enough of stimuli. Again, we have in this case we are dealing with 16-year-olds, 15-year-olds, and some of our guys play 30 minutes, sometimes they play 35 minutes, sometimes longer. So we need to think about kind of normalizing the game and also taking into account the game duration. And what we are trying to do is to also try to calculate what will be the 90-minute game performance and then compare it to that. So we're basically normalizing the game based on the duration of the game or minutes played per individual, and then we also use that across multiple games to give us a glimpse of the hardest session, and then we use that to normalize the session. So we can see again what session is hard, what session is easy. Training stress balance is again continuation of the topic. I've been writing about it in the last couple of blog posts, and a lot of things. Actually, the first time I saw this comes from training and racing with Powermeter, and which basically confirms that we need to read stuff from other sports to kind of maybe try to find an idea how to use it. Training stress balance is nothing fancy. It's basically two rolling averages. One is called chronic rolling average. Basically something that lasts from 3 to 6 weeks, and it gives us the idea of the baseline, basically saying this is the training load that athlete is used to, and following this chronic training load might tell us if you're actually slowly increasing the training load or the training load is decreasing. The acute training load is something that's shorter, maybe 5 to 14 days, and it gives us as the name suggests, the acute training load. So it gives us what's the recent training load the athlete is doing, and by comparing the two, by comparing the chronic training load and acute training load, we might see if we are overloading our athletes or underloading our athletes, and it can give us some glimpse about are the athletes going to be affected by a sudden increase or sudden decrease with the acute training load. For example, the sudden decrease in acute training load might peak our athletes, so they might depending again what happened in the history, so they might taper and peak, but in the long run, the decrease in a acute training load is going to bring the chronic training load down, and that's going to cause detraining. Again, this is just like a very simple way to give a quick analysis of the training load and give you a little bit bigger picture, and maybe give you some insight about your training. Maybe something's doing wrong, or given training is, or given athlete is underloading or overloading over time. Yeah, going back to a training stress balance quickly is one thing I forget to say is with every training, with every model, is important to know the assumptions of the model. And I've been saying in the last couple of blog posts, which you can find online, is that it's very important how the model deals with the assumptions, and if the coach understands the assumptions. Again, goes back to the allegory of the cave, Plato's allegory of the cave, because we need to know this is not real world. This is representation, and we need to know how the model is dealing with some of the stuff happening in a real world. And in this case, that might be days off or missing data, and how's that going to affect our model? And that's happens all the time. So we need to understand the assumptions of the model to be more prone to making any errors. Bannister impulse response model could be considered as a continuation of a training stress balance. I think the first time I heard about it was a long time ago, but the best article I read about it, actually one of the best articles, applied articles I read regarding the performance analysis is from David Clark and Philip Skiba, and it's freely available online. So this is just a picture from the article. Similar to acute and chronic training load, we are looking for from positive training effect and negative training effect, which are familiar as a two-component adaptation model of fitness and fatigue. And we are trying to find we are basically trying to find the model that links the training load we are doing with the training effects we are doing. In this case, training effects could be anything. Could be increases in maximum aerobic speed. Could be actually the game performance. So with the previous case, with the training stress balance, we are just kind of quantifying the training load, and we are choosing the different rolling windows. So as I said, it could be 4 days, it could be 14 days for acute, and it could be something longer for chronic. But we are just using some number we just selected as a useful. But with Bannister model, the Bannister model actually is trying to optimize. So the Bannister model is trying to optimize the formula behind the positive training effect, negative training effect, so it can explain the variability in performance. And again, that can give us something that's prescriptive. And you can find much more in the mentioned article by Clark and Skiba, and I highly recommend checking that article because it also deals with critical power and other very interesting mathematical models. So again, Bannister model trying to find a link between the training load we are doing, or in this case impulse, and the response we are getting. We know, as a coaches, we are usually doing it this more intuitively because we know what we are doing, and then we know what we are getting. But if you are not getting what we want, we're probably going to switch training a little bit. But it's more trial and error. In this case, Bannister model can do it more mathematically and can help us with giving us some insight to what training the athlete needs to respond, and maybe what should be the duration of the overload, what should be the duration of the taper. Again, as with any other model, all models are wrong. Some are useful, and all models have assumptions we need to understand. And same thing with the Bannister impulse response model. There are a couple of flaws in the model, but it can give us something useful. In this case, individualizing training load for a given individual. Injury prediction is another interesting use of the GPS. I'm not going to spend much time here, but again, as similar with the Bannister impulse response model, we are trying to predict increase in performance. So what training load is gonna increase the performance? Either physical qualities, maximum aerobic speed, 1 RM squat, and yada yada yada. But we can also say, is the training load we are doing can predict the injuries? And again, this is, I would say, some ethical thing, because to predict the injuries, you need to have the injuries. You cannot predict something that's not happening, because in machine learning, that's called supervised versus unsupervised learning. With supervised learning, we have a target variable. In this case, it might be injury occurrence. So we are trying to predict injury occurrence from another variables. But with unsupervised learning, we don't have this target variable. So we don't know what we want to predict. So we just want to see if there's a pattern in the data. And some pattern in the data might indicate that we are doing, we might be overloading things. And so again, it comes back to, should we allow the injury to happen for our models to be precise? I don't think so. So it's not ethical. And most of the clubs that use GPS, sometimes they don't intervene with the GPS for a first year. So they're probably using a first year to build up a data. And even if they see actually the pattern in the data that might indicate overload or something different, something is different, they might not intervene. So, and then if that results in an injury, that's very important for the algorithm to learn what's important to predict the injury. But again, I'm not so sure it's very ethical. And with the duration of the training contracts we have as a strength conditioning coaches, I don't think you're going to have 5 years to allow such a thing. And I don't know if you're going to have a lot of athletes to afford it also. So if you have some historical data about the injuries, it might help. But if you see things happening, I think we need to intervene. And again, it depends. Are we making a model for a group? Because model for a group, again, might be less precise than an individual model. So again, each individual is different, and we are trying to individualize the training. We might get some indication about what might bring to injury from a group model, but to be really precise, we need to build a model for each individual. Which brings me to Nassim Taleb again from Antifragile, and I like his quotes on prediction. He's basically critiquing a lot of guys trying to sell you any prediction algorithms and try to predict rare events, as he likes to call them, black swans. And black swan in sport world is a probable injury. So I like this quote, and I think that's something that we really need to think about. Is that it's far easier to figure out if something is fragile than to predict the occurrence of an event that may harm it. So instead of trying to predict the injury based on the data, we might be easier and more precise by predicting who of our players is fragile. So something to keep in mind. Return to play. After we are injured, we want to return to play, right? Again, I'm not going to spend much time here. There's a great chapter in High Performance Training for Sports. This is actually a table from the chapter. And we usually, actually, in this case for return to play, we should have something as simple as a checklist to be sure that athlete is able to perform at least to his baseline or very close to his baseline before going back to the real training. That's why we sometimes take, as it might seem, a useless measures in the preseason. Let's say a groin squeeze, I don't know, even FMS or something similar, some similar screening. It might not give us any usable thing to create training, nothing prescriptive, but it can help us when the athlete gets injured, and we want to see if he's coming back at the same level, and it can give us some safety, so we can say, okay, now he's ready to go on the next step, and we should create that type of a checklist. For example, even MRI, the richer clubs can do MRI for most common injury locations, so they have a baseline when the injury, if the injury happens, so they can help the player come back quicker. And GPS load also have a role in that. So once the player is ready to start training, we need to make sure he's ready. He's slowly building up the training load as he's doing before the injury happened, and he's actually slowly building up to the game demands. And having a GPS is just a way to help us out and easily quantify this task. And this is a little bit more advanced, testing without testing. I think last two topics need to watch on time. So testing without testing, this is something that very intrigues me, and this is something I wish I can spend more time on, and especially in the near future. Again, it comes from this awesome book, Training and Racing with a Power Meter. Because we collect so much data almost every day with the GPS. The athletes are wearing the GPS all day. So why do we need to do a testing, like maximum speed test? 5 minute shuttle runs, yo-yo tests. Why do we need to do it? Can't we make any claims from the large amount of data we collected about the physical qualities of the player? Again, we need to assume that the GPS is valid and reliable and sensitive. And again, we also need to keep in mind that something that we want to use in this case is the rule of big numbers. So if we keep track of a training for a couple of weeks or a couple of months, we might see we're probably going to see occurrence of a maximum sprint. So why do we, maybe we can use that as our indication without actually testing the players, because they are being monitored all the time. Maybe we see a performance that the player is covering a lot of ground in 5 minute interval. Maybe we can use that to make any claims about his physical state. Again, it might depend from sport to sport. Some sport might actually put more constraint on your expression, on your physical qualities, and in some sport it might be easier to make any claims from a training data to a physical qualities, and in some sport might be harder. I don't think this is a topic that's being discussed a lot, and I think it deserves much more of our research and actual implication in practice. Let me show you how is this done. Yeah, I call this time profiles. Someone might call it power duration or velocity duration profile. In this case, this is this is a random data I generated, or actually it's a real data from one sample of data. In this case, it's a metabolic power, something that I'm going to talk about a bit later. But it could be anything. It could be velocity. And as you can see, this is quite chaotic, right? And what we try to do is to create rolling windows of different duration. For example, if we create a rolling window of 5 seconds and roll it across, what we might want to find is the highest average, in this case metabolic power, but might be highest average velocity in those 5 second window. So then we know what's the highest velocity, what's the highest average velocity athlete produced in 5 seconds. And if we apply, again, I'm not going to go into different ways to filter and average. And again, we can use Skiba spike score algorithm or something like that to take into account short bursts of velocity or acceleration or power. But if we repeat this for different window durations, so 5 seconds, maybe 10 seconds, 15 seconds, we might get something that I like to call velocity time profile, or power duration or velocity duration profile. And it might look like something like this. This is actual result of the above picture. And you can see this, the maximum average power across different rolling windows. What this says is that this player generated a certain amount of power for 2 seconds, and then we can see that his maximum average power is dropping as the rolling window increases in duration. So from this very simple graph, you can calculate maybe his maximum sprinting speed, his in this case 5-minute maximum aerobic velocity, and this dotted line is critical power in this case, which is a concept again from the concept you can read more about in mentioned article by Skiba, and that's basically the velocity that can be sustained for a lot of time. And here's the catch: if you keep tracking the GPS data across weeks, and if we try to apply this algorithm across all our data, we might get this power duration or velocity duration profile. It's similar to force velocity or power velocity profile we have in strength training. It gives us it can give us the complete profile, energetic profile of a player, and we can also compare maybe January to March or something like that, and we can probably see the shift. And again, the shift might result from actual change in the physical qualities, or the shift might actually be a result of the change in training. Again, we need to use our domain expertise as a coaches, and then see, is this related to a different drills, or it is actually related to a change in athlete qualities. So we are achieved to test the athlete, get some insight about his individual qualities without actually testing him. Probably going to finish with metabolic power. It's quite interesting area, quite new. Basically, it comes from very simple idea that let's say we do a 40. This picture is actually from a book by I can't remember. Hopefully, no one's gonna charge us for for using the material. So this is just a velocity across sprint. So if I do a 40-yard maximum sprint, my velocity change like this. But for example, if I use in this case, this is 4 4 yards per second. Let's say I use 4.5 yards per second. It might correspond to maximum aerobic speed, or maybe 6 that might correspond to high velocity running. So all my efforts as an athlete that was done under 5 yards, or in this case might be 6 yards, will not get caught by this velocity bin. So all these short movements, quick movements that are happening in a small space will not get caught by this traditional way of doing time motion analysis. In this case, using only velocity, because I'm not going to reach the threshold of the velocity. What we are using now is also we try to use acceleration, because in first couple of meters acceleration is going to be huge and it's going to slowly drop. So we might combine the acceleration data with the velocity data. We can use that as a different GPS metrics. So we might say how many maximal accelerations as a number. We might say how many, what's the distance doing high intensity acceleration, what's the time doing high intensity acceleration. But what we can do also is we can combine acceleration and velocity to get these actual physical stress, and in this case it's called metabolic power. So even if I'm not running fast, for example, if I do a long jump, standing long jump, I produce tremendous amount of power. But if I just track velocity, then at the end of the session, it might seem that I did an easy session because I didn't spend a lot of time in high velocity zones, but I created a lot of power. Something that we also don't keep track in team sports is this vertical directions, the jumps, headers. We don't keep track that. We only keep track of the 2D, basically forward, backward, left, and right. So metabolic power is a way to kind of integrate all of that and give us the kind of integrated stress, integrated load on an organism. It started, I think, a couple of years ago. We still don't have, as far as I know, hopefully someone might correct me, we don't have a valid and reliable way to calculate it. There are different formulas to calculate the metabolic power from acceleration and velocity. So again, it might be very useful because it helps us quantify high power performance, but it also might help us with the modeling, and we can use it in using it as a critical power and a W prime. Again, try to check the Skiba model. So if using a metabolic power approach, we can what we are looking for is to see basically the critical power is the highest power that athlete can produce for a long amount of time. It's very useful in endurance sports. In endurance, they might use critical velocity or critical power. It's used in rowing, cycling, and running. And we also have W prime, which is an aerobic reserve. So in this case, we can use 3 shuttle tests, and since we are able to calculate the metabolic power, not only speed, we get this the real load that athlete is performing, and we create critical power and velocity profile of the player. So we can use again 3 tests, maybe starting from 30 to 60 seconds, 5 minutes, and 10 minutes, and using a simple formula, we can calculate critical power and W prime. Again, we can use this, or we can use testing without testing, as shown in a couple of previous slides. Again, critical power and anaerobic reserve is something that we actually use intuitively as coaches, and it's again very similar to force velocity. It can give you a full energetic profile of the player, and as an extra thing, it can be useful in It's something that I like to call real-time fatigue assessment. And this is very, very novel. We keep trying to assess the fatigue real-time in a game by first we start with the heart rate, and I don't think it's any useful. So we might say, okay, the drop in the heart rate drop might indicate the fatigue, or the heart rate increase might indicate fatigue, but without considering the actual performance, it cannot tell you much. And next step forward, we started using velocity, and we tend to see in a game, we tend to see in the last 20 minutes, 15 minutes, we tend to see the drop in physical performance, but we never know, is it because the athletes are tired, or there's a change in tactics in the last couple of minutes of a game. And this can actually help. Filip Skiba started doing this with the cyclist, very promising, assuming that we get the metabolic power equations correct, and all other GPS metrics are valid and reliable. And this is something that I think I might start more experimenting or more researching. So this is a picture from a Filip Skiba article. Again, we have instantaneous power on across time. So this is cycling, and if we know instantaneous power, or in this case might be metabolic power, and if we know the critical power of the athlete and his anaerobic reserve, we might model how much he's wasting his anaerobic reserve. And again, when the player is over his critical power, he start taking his reserves. He's like Fast and Furious. Your car can reach so much velocity, but you can start using nitro and get extra boost, but you're basically wasting the nitro, and you don't have a lot. And W prime, or anaerobic reserve, can tell you actually how close is player to actually using all his nitro. And we assume that when someone spends all of his anaerobic energy, he's reaching the fatigue. One thing with anaerobic energy, anaerobic reserve, is that once a player is performing below his critical power, he start kind of replenishing it. And then one thing we need to know with the player to make such a modeling is to know how fast he's replenishing his anaerobic reserves. And taking all of this into account, we can probably make, and assuming, for example, in soccer that FIFA will allow real-time tracking during the games, we might give some indication when to change a given player. So again, comes back to that first picture of giving a practical advice to a coach. This guy is probably very tired, try to change him. And with this, I think I'm finishing my presentation. Hopefully you guys are still awake, and hopefully you pick up some interesting things. Brendan, you mind taking over and maybe giving me some of the questions if our listeners have?
Yeah, absolutely. That's fantastic. Thank you so much, Mladen, for that. And everybody listening in, clearly a genuine expert in this subject. And if you've got any kind of aspirations to really get to the cutting edge of the field from a monitoring perspective, but also just in general as an S&C coach, sports scientist, please do ask your questions here for Mladen. It's great stuff. And just one from me to get the ball rolling a little bit. In terms of, you've talked a lot about GPS there, obviously, and for environments that don't potentially have the same level of funding, what kind of monitoring would you be looking to put in place in a kind of team sport environment, and just to give us some usable data? I know obviously we can do things like your classic kind of yo-yo tests and things like that, but just from a recovery perspective and a workload perspective, what are your thoughts on just implementing something from at the grassroots level?
Usually everybody recommends Session RP as a cheap solution. I'm not that big fan of it, to be honest. Again, depends on the culture and how much you can trust your players, and again, if, for example, taking Session RP into consideration as something that people suggest as a cheap, actually free solution, and that corresponds with the training load defined by heart rate, or in some recent papers, it correlates with the GPS data, the GPS load. There's a great read in Thinking Fast and Slow by Kahneman, and they show that we are not that very well when we judge subjectively the hardness of or the pain of a given event. And what we usually do is we take the average, and this is subconscious. We take the average between the hardest part of the session and the latest part. So, for example, if you have a same session and someone plugs in the extra conditioning at the end, or maybe very fast sprint, maybe 30 seconds, the players will, or for example, if you have A session and B session, and this hard sprint is done as a first thing in a session, and everything else is equal, and then we have a session B where everything is equal, but we put this hard effort at the very end. Even if the two sessions are same, athletes going to rate them differently because the most painful experience was happening at the end.
Yeah,
so yeah, exactly. So I'm not so sure that Session RP is the best tool. Again, depends on the culture at hand. Maybe a lot of coaches use it as a cheap solution. Another thing I like a little bit better is these wellness questionnaires. Basically 2, 3, or 4 questions, very simple on a Likert scale from 0 to 10 or 1 to 10, and just saying how you feel, and those sort of things can give you indication of how the athlete is adjusting. But again, we have people that are low raters and high raters, and I think the best thing is to actually talk to a player, and this can give us some historical value. For example, when I was in Hammarby, Greg, when he was a coach there, he asked me like, why do we take these questionnaires? Why can't I just call the player inside and talk to him? And I said, basically my response was, although he's right completely, is that you cannot talk to all 30 players every session, and the other one is you probably don't remember what the player said 2 months ago because you're not measuring it or saving it. So using these simple tools as a subjective is very very simple and is basically free, but it has its own glitches. We are all irrational creatures, and we need to take the context into account and the culture in the club when we evaluate those things that the player says. Even if you talk to them face to face, they might say, "Yeah, I'm feeling perfectly fine, and he's underperforming. He's going out. He's not sleeping." So again, there's no free lunch.
Yeah. No, I get that. Fantastic. Guys, are there any more questions for Mladen before we complete this talk? We've got an opportunity to get the best out of Mladen while he's on the line with us. What are your thoughts on utilising this GPS data with like kind of youth populations, and do you get into that much with the younger athletes, or do you kind of give it more to the more senior athletes?
currently in Aspire, all our squads, starting from I think 14, use the GPS.
Yeah.
And again, as in my introduction, assumption part and planning part, we are still struggling with the bottom-up approach, how to best use it, how to best deal with the storing the data and everything else. And once we sort that out, we're going to start using the top-down approach and basically saying, why are we using that data? And again, let's go back to the elephant in the room. I will put a lot more things before actually quantifying the training as more important. And a lot of coaches, it's just like an arms race, irrational arms race. Clubs are just buying technology in the hope to compete with their competitions. Just because they bought it, I need to buy. But I would say a lot of different things are much more important than just quantifying training and showing nice charts. Again, if you have the manpower and finance, you can do it. Why not? You can do it. But again, the point is how you're going to use it. How's that going to affect your practices? And is it needed? And to be honest, I'm not so sure. Is it really needed in a low level sports? Again, other things might need to be considered before implementing such a technologies.
Yeah. No, that's a great answer, and I think that's a fitting point to kind of wrap up the talk. Any references? Another question here that you can, for software platforms, books, you can point to in regards to machine learning, and that's from Hani Assi.
There's a very, very good book by, they have weird names. It's called Introduction to Statistical Learning. It's free online. You can download a PDF, and it's great introduction. And I like to see as machine learning compared to statistics. The main difference is that machine learning is more into making more precise predictions and less comprehensive, less understandable models, although it can happen. So, and statistics is more about making more inferences and making more understandable models. But a lot of things that happen in machine learning happen with the increase in the power, in computational power of the computers. And I would say because with machine learning and data analytics, people are actually trying to solve real life problems and real business problems. For example, it's being used a lot in Amazon. If you click on a book and it gives you suggestions, this might you read because other people's liked it. So with machine learning is more kind of is started to actually solve the real questions. So even as like a child or very similar to statistics, I think machine learning might help us more in training, and just disregard the p-values and all that stuff that researchers use. That's written for people who are reading the papers, research papers, and coaches probably not reading the research papers. So using machine learning might give us something that's actually solving the day-to-day problems in coaching.
Mm-hmm. Yeah. Okay. I've got a question from Craig here on youth GPS. Do you use absolute values the same as adult sport thresholds or individual-based values to assess data?
Yeah, that's a great question. That's a great question. And as I said, the cutoff we use, they basically started with the first researchers. They just said, okay, low intensity is below 14 kilometers an hour, medium is 19.3, and high intensity is over 25. So that's a great question because it might differ based on a age. Maybe a way forward might be to use relative thresholds, as I said, although they also have a problems. but the solution might be to use something that take a snapshot of all the accelerator, or basically in this case we're talking about velocity. You can take the snapshot of the velocity during training. For example, bike score by Skiba takes a couple of I think exponential rolling average squared on a fourth degree, and then average, and then take the fourth root, and it kind of gives you also the it's also affected not only by average, but it's affected also by very high intensity sprints. So it gives you better snapshot. And again, it comes back to a thing I said, like we can use bins, but maybe we can use also the relative, and maybe we can use this like a metric that gives you a snapshot of the, let's call it a velocity load of the training. Again, great question, and actually something that I haven't thought about. Thanks for asking that. And yes, some of the assumptions of the models as well.
Yeah, fantastic. All right, well let's wrap things up there, and I want to say a big thanks again to Mladen for that fantastic talk, and thanks to listening in everybody at the conference. I know you know it's taking all this time out of your week, but it's fantastic knowledge and educational material to get to improve you and improve your coaching practice. So thanks again for that. We will be back in just about 2.5 hours at 6 p.m. Greenwich Mean Time for Alan Ruddock's talk on Knockout Power Simple Science. So Alan's a great presenter and a great sports scientist as well, and he's going to really show us how he's bridged the gap with science and coaching practice as well with the combat athletes and the other athletes that he works with. So please do tune in for that. We'll be online just before 6 p.m. for that talk, and then we're going to finish the evening with a really interesting presentation from James Clare on building habits. And James is really a popular and expert speaker on this particular area, having developed such a powerful following through his blog at jamesclare.com. So looking forward to that later on, and thank you for listening again to that, and Mladen, thanks very much again, appreciate it.
Thanks for having me over, and thanks for the listeners for listening. Hopefully they pick up some a tip or two. If you have any further questions, I'm happy to answer them at complementarytraining.net. And again, I'm not expert in this area. Still struggling, trying to be a bridge and learn from both disciplines, from both what coaches need and what analysts can provide. Hopefully you pick up something useful, and thanks for listening.
Thank you. Thanks again. Great, mate. Let me just hang on the line there, Mladen.
Yep.
Thanks again, mate. That's great.
Yeah, thanks a lot. Hopefully not too boring. I think it's a lot of things to cover. We cannot go.
Great, mate. No, I appreciate it. And it's like it's never as sort of a sexy a topic as kind of